we are moving into the next example. Evaluate the Ito integral, integration between 0 to t, wt dwt. That means the integrand is wt, integration with respect to wt. So we can use the partitioning the interval 0 to capital T into n pieces, n parts. Then as a limit n tends to infinity, this is not, the integration is nothing but limit n tends to infinity of I is equal to 0 to n minus 1 w of ti and the difference of w's. So the same definition we have given in the Ito integral also. So here the Ito integral is well defined because wt, that is the integrand which is adopted, and also the mean square integrable. Therefore this is Ito integral. So the I of t is equal to 0 to capital T wt dwt, that integral is the Ito integral. But here we are going for the upper limit is a capital T, not the variable limit. So for each I, the way we have written limit n tends to infinity summation with the difference of w's I and w's, and this is a w at the point ti, and whereas this one is a w of ti plus 1 minus w of ti. Therefore these two are the non-overlapping w's. So the increments are independent. Therefore w of ti and w of ti plus 1 minus wa are the independent random variables, or having the normal distributions. We are using the property of Brownian motion. Therefore w of ti and w of ti plus 1 minus wa are independent random variables. So what I am going to do here, let pi be the set of all finite subdivisions of pi of the interval 0 to capital T. Therefore first we will find out what is the q of pi. That is different from what we want. What we want is different. What we want is limit n tends to infinity summation I is equal to 0 to n minus 1 w of ti with the difference. But what we are defining now, q pi I, is nothing but the difference whole square. But what we want is this w of ti with the w of ti plus 1 minus wti. So we started with the q pi, that is equal to the difference whole square. The difference whole square is the same as suppose you treat this as a, this as a b. So a minus b whole square is same as a square minus b square minus 2 times a b minus sorry, a minus b minus 2 times b a minus b. So if you simplify, you will get a minus b whole square. But if you expand the summation now, this will be only the last term will be there and all other terms vanishes. So therefore you will get a w of t whole square minus w0 whole square. The last term and the first term will exist and all other terms will vanish because of minus squares. Whereas this one, minus of 2 summation w of ti multiplied with the w of ti plus 1 minus w of t. That's what we want as a n tends to infinity. But we know the result, limit norm of pi tends to 0 of q pi will be capital T. That we have discussed in the lecture 1 when we discussed the quadratic variation of Brownian motion. In the lecture 1 we have discussed the quadratic variation of Brownian motion, in that q pi is defined, limit norm of pi tends to 0, the q pi will be capital T. Therefore what we want is a limit n tends to infinity of this quantity, and that is in the third term in this q pi. So now you apply limit n tends to infinity in this equation. So the left hand side becomes the capital T. The right hand side becomes a Wt whole square minus W0 whole square. You know that W0 is 0 for a standard Brownian motion. Therefore, you will get only the first term. Second term will be 0. Third term is the unknown. That's the integration. Limit n tends to infinity of summation. That is nothing but the I of t, I of capital T. Therefore, 0 to capital T Wt dt, that is nothing but in the left side we got a capital T. Therefore, you will get Wt whole square minus capital T is equal to, since it is minus 2 times, therefore it will be by 2. Hence, the integration 0 to capital T Wt dt becomes a Wt whole square minus capital T by 2. So here we have used the quadratic variation of Brownian motion is capital T, that we have used for the interval 0 to capital T. Therefore, the integration is 0 to capital T. So we have used the Brownian motion quadratic variation between the interval 0 to capital T, that is capital T. Therefore, the integration is going to be W of capital T whole square minus capital T by 2. Hence, this integration is Wt whole square minus T by 2. We see that unlike Riemann integral, we have extra term capital T. If the integration is with respect to bounded variation, differentiable function, then you won't have the term capital T here. Just it is a Wt whole square by 2. Suppose you replace Ws by x, therefore you will get a 0 to capital T x times x dx, that is nothing but x square by 2. Whenever the integrand is a bounded variation as well as a differentiable function. That is nothing but the Riemann integral. So in the Riemann integral you won't have the extra term capital T by 2. But here we have the extra term minus T by 2. So this arises from the quadratic variation of a Brownian motion, which is finite. Whereas if it is a real valued function which is bounded, then the quadratic variation is going to be 0. But here the quadratic variation which is a finite value, therefore you are getting minus T by 2. So the above next remark, the above integral is defined not only for the upper limit integration capital T, but also every upper limit of integration between 0 to capital T. In this integration, we have done the upper limit is capital T. Therefore, we have used the quadratic variation of Brownian motion between the interval 0 to capital T, that is capital T. But instead of that, we can go for variable small t also. In that case, here we have to use the quadratic variation of Brownian motion between the interval 0 to small t, and that will be small t itself. That's a variable t. Therefore, this integration will be 0 to small t, ws dws is nothing but wt whole square minus a t by 2, where both the t's are small letter variable. You see, the construction of Ito integral is similar to one of the Stieltjes integration, but instead of integrating with respect to the deterministic function, the Ito integral with respect to the random function moves precisely path of the linear process. So that is the difference between the Ito integral and the usual integral. The usual integral is with respect to the deterministic function, whereas in the Ito integral, the integration with respect to the path of Brownian motion or linear process, which is unbounded variation and nowhere differential. Therefore, the whole integration is different.
Consider this stochastic integral
In this, the first integral is a Riemann integral of a stochastic integrand, whereas the second integral is a Ito integral. This equation is very useful in finance. In the Black-Scholes model for pricing, the stock price is assumed to follow geometric Brownian motion. Now we are discussing the few properties of Ito integrals. Still we have used a few properties in the examples, but now you can understand how the properties will be used in the examples. The following results holds by the Ito integral defined in the equation 1. In the equation 1 we have discussed this is the Ito integral which we have discussed in the first equation. So, this we are referring. Yes, the first property, the integral I of t is a martingale with respect to the filtration f of t. This is a very important property. If you have a Ito integral, that means the integrand is adopted and mean square integrable, and the Ito integral is a stochastic process, and that stochastic process is having the martingale property with respect to the filtration f of t. The same f of t, the integrand is adopted also. With respect to the same filtration, the integrand is adopted also. So, the proof is you have to, if you want to verify the stochastic process is martingale, you have to check three properties. The first property is it has to be first the stochastic process for fixed t, it has to be integrable. Then it has to be adopted. Then the third property, the conditional expectation has to satisfy the equality property. So, if these three properties are satisfied by the stochastic process, then we say the stochastic process has the martingale property. So, here I of t is a stochastic process for t greater than or equal to 0. So, first we have to verify it is integrable. So, you can find out the expectation of I of t for every t, that is going to be a finite value. Then the second one, I of t has to be a, for fixed t, I of t has to be a ft measurable, that is adopted. So, for fixed already the integrand is adopted, the integration with respect to wt, and the wt is also adopted to f of t. One can prove the I of t is also adapted to the filtration f of t. The third condition, expectation of I of t given f of s, where s is less than t, that is same as I of s. You have to prove expectation of I of t given f of s, where s is less than t, that is equal to I of s. If that is proved for all t, since these three properties of martingale is satisfied, I of t will be a martingale with respect to the filtration f of t. Here I am not discussing the proof. Here I am not giving the proof, but I have discussed what are all the properties has to be verified. Second property, expectation of I of t, that is same as the expectation of 0 to integration, the definition, that will be 0. Since it is a martingale, it will have a constant mean. Therefore, expectation of I of t is same as expectation of I of 0, and you know how to evaluate expectation of I of 0, that will be 0. And the third property, expectation of it whole square, that is same as expectation of 0 to t x square ds, that is same as expectation of integration 0 to t expectation x square s ds. So the expectation and the integration interchange the place. This is called the Ito isometry. So this is a very important property of second order expectation, that is the integrand, and earlier you have expectation of I of t whole square, that is nothing but integration 0 to t expectation of x square ds. This is nothing but the Riemann integral. For fixed s, the expectation of x square s is the function of s. So you are integrating 0 to t, the integrand is expectation of x square s ds. So this is nothing but the Riemann integral. Now based on the property number 2 and 3, you can conclude variance of I of t is nothing but 0 to t expectation x square s ds. Because the expectation of I of t is equal to 0, expectation of I of t is equal to 0, therefore variance is nothing but expectation of I of t whole square minus expectation of I of t, variance of I of t is equal to expectation of I of t square minus expectation of I of t whole square, that is same as 0 to t integration expectation of x square s ds. One can find the quadratic variation of I of t also, because I of t is a stochastic process. So you can find out the quadratic variation between the interval 0 to t. So I comma I between the interval 0 to t, that means a second order variation between the interval 0 to t for the function I of t. I of t is the Ito integral, whereas the quadratic variation is nothing but integration 0 to t x square s ds. So this is the Riemann integral. So I have not given the proof of the fifth property also. We are just stating the results of Ito integral, and we have used a few properties in the examples. The Ito integral is a random variable for all t, for all w belonging to omega. Therefore, you can write down I of t of w, that is nothing but a limit n tends to infinity, the value of x of asi, the difference of w's. You know that x is a random variable, the difference of w's is also a random variable. Therefore, for fixed n, this summation I is equal to 0 to n minus 1 will be nothing but a random variable. And you are finding limit n tends to infinity of this summation. Therefore, actually the convergence takes place only for the subsequence. That means I of t is a random variable, and that random variable is nothing but the convergence of the right hand side limit n tends to infinity of this summation. And its integral depends on the sample path, because you are finding the difference of w of si plus 1 minus w of si. Therefore, this integral depends on the sample path. And also, we need this following properties. The d of wt dwt will be dt, that is nothing but the quadratic variation of Brownian motion is nothing but a finite value. If you are finding the increment between the interval 0 to t, then the quadratic variation is small t. Whereas if it is a real valued function, which is a differentiable, then dt, the quadratic variation of the function t will be 0. And the mixed variation, cross variation, dwt with the dt, that will be 0. So if you find out the quadratic variation with the wt, that will be the t, whereas the quadratic variation with the function t will be 0 and the cross variation will be 0. So this result will be used when you are finding the I of t. Here is the important references for the Ito integrals. In the next class, we will consider the Ito formulas.